Hello, in this video we will talk about data warehouse design and dimensional modeling. Many organizations need to create the data warehouse used for decision support. Two competing approaches are employed. The first approach is that of Bill Inman, who is also called as the father of data warehousing. This approach is a top-down development approach that adapts traditional relational database tools to develop an enterprise-wide data warehouse. So it's also called as an EDW approach or enterprise data warehouse approach. This approach focuses on several subject areas, which will be the subject areas for data warehouse. It is usually very costly and takes a long time to develop. Another approach is suggested by Kimball, and this is called as the DM or data mart approach. The strategy for the DM approach is plan big, build small. A data mart is a subject-oriented or department-oriented big data warehouse. It is a scaled-down version of a data warehouse that focuses on the request of specific departments, such as, let's say, marketing department or sales department. This model applies dimensional data modeling, which starts with tables. So which model is the best? There is no one-size-fits-all solution. Ideally, you would like to get to the enterprise data warehouse approach so that it can support multiple functions within the company or entire enterprise as a whole. But it is costlier and takes a long time to develop. While Kimball's approach is simpler and is frequently a convenient first step to get some experience in constructing and managing a data warehouse, while presenting the business users with the benefits of the data warehousing concept. They can see that this is beneficial and may be ready to invest in it further and go to the EDW approach. Once you decide to either build a data warehouse or a data mart, the next step is to actually go ahead and design the underlying structure of the data warehouse or data mart. For this, you need some data model. The design of data representation in the data warehouse has always been based on the concept of dimensional modeling. A dimensional modeling is a retrieval-based system that supports high-volume query access. It results in a data model for the data warehouse or data mart to be implemented. It is very much like the ER diagram that we use for designing a database. Star schema and the snowflake schema are the means by which dimensional modeling is implemented in a data warehouse. The star schema is the most commonly used and the simplest style of dimensional modeling. The star schema contains a central fact table surrounded by and connected to several dimension tables. The snowflake schema is a logical arrangement of tables in a multi-dimensional database in such a way that the entity relationship diagram results looking very similar to a snowflake. And you can see again you have a fact table in the center connected to several dimensional tables. So the fact table contains a large number of rows that correspond to observed facts and external links and foreign keys. So foreign keys are going to be connecting them to the dimensional tables. A fact table contains descriptive attributes needed to perform decision analysis and query reporting. So for example, each one of these is a descriptive attribute. Surrounding the fact table, we have all of these dimension tables, which are linked with foreign keys to the fact tables. The dimension tables contain classification and aggregation information about the central fact rows. Dimension tables contain attributes that describe the data contained within the fact table. So let's say if it was the first dimension, it could be, let's say, product. Then we have a product dimension table which describe the attributes of that product. So the dimension table address how the data will be analyzed and summarized. When we write the queries, the dimensions are used to slice and dice the numerical values in the fact table to address the query requirements. For example, we may be asking, let's say if this was a sales fact table, we may be asking something like how many items are sold per week or per month, like that. You may like to note here that fact table are connected with several dimension tables, and fact tables contain facts, which is each one of these fields, and some of these fields are acting as foreign keys to connect them to dimension tables, and others are measures. So fact table can contain facts, some of which can be measures. Dimension tables contain dimensional attributes. So let's look at the definition of these terms real quick. Facts are the measurements that result from a business process event and are almost always numeric. So the contents of fact table are mostly numeric. A single fact table row has a one-to-one relationship with the measurement event as described by the fact table's grain. A measure is a numerical property of a fact and describes quantitative fact aspect that is relevant to the analysis. We'll discuss examples of this later on. So what is a grain? The grain or the granularity of the fact table describes the level of detail in a fact table. The dimensions provide the who, what, where, when, and how context surrounding a business process event. The dimension tables contain the descriptive attributes used by the BI applications. Usually, dimensions are the nouns describing objects that participate in the business. Dimensions may be hierarchical or they may be denormalized. Here's an example of a star schema. It is a simple database design in which dimensional data are separated from the fact or event data. Another name for star schema is also dimensional modeling. The star schema is composed of fact and dimensional tables. If you have any experience with database, you may see that fact table is like an associative entity that connects or joins various dimension tables. So the fact tables contain factual or quantitative data, and the dimension table contains description about the subjects of business. So a lot of qualitative data or categorical data will be in dimension tables. There is one-to-many relationship between dimension tables and fact tables. Means one row in the dimension table may be associated with zero-to-many or one-to-many rows in the fact table. So how do we indicate this relationship? On the dimension table side, we will have these two dashes cutting this line, indicating this is the relationship. On the fact table side, if it's going to be either zero or multiple records, we indicate it with a zero or many symbol. If it's one or many records in this table, we will indicate this with a crow's foot with one dash on the line, and then two dashes on the dimension table side. The difference between these two is that in the first case, in this case, one row in the dimension table may not have a related fact table. For example, if this was a product and this is sales, then maybe if there is a new product which has never been sold, we may have zero rows associated with it in the fact table. In the second case here, let's say what it means is that each row in the dimension table will have at least one row in the fact table or many rows in the fact table. So this is mandatory. The dimensional tables are denormalized to maximize performance in case of a star schema. What that means? Normalization basically is a concept that we use in databases that lets us organize the tables such that we reduce redundancy in the data. So if there was a hierarchy in your data such that you had an address with zip, city, and state, you do realize that one city can have multiple zips, and one state can have multiple cities. So this is a natural hierarchy in your data. Usually, if you are dealing with database tables, a lot of people like to store these fields in separate tables, as one table will be state, one will be city, one will be zip. That way, you don't have to repeat that information in all the tables. This is the concept of normalization. So when you denormalize, it means you will ignore this hierarchy and put all of these three fields in the same table. So we use denormalized data within dimensional tables if we are dealing with star schema. So that's what we mean by not taking into account the hierarchy. This is done for the simplicity and performance. That way our queries will run faster with the help of a star schema. Another thing I want to highlight here is the concept of primary keys and foreign keys. So in the dimension table, they are connected with the fact table using for primary keys and foreign keys. So the primary key of the dimension table is being repeated again or being reused in the fact table as a foreign key, so that these two tables can have common field based on the data of which common field these two fields can be connected, or based on the matching data we can join these two tables. Just to help you understand the concept of primary keys and foreign keys, think about your own nationality. Let's say you are a US national. In your home country, you are a primary resident. But if you, let's say, travel, you go to New Zealand, there you are a foreigner. So primary resident, foreigner. That is what we are doing with this column key 3 here as well as here. So we have 1, 2, 3, 4 different foreign keys because fact table is connected to 4 different dimension tables. So all of these primary keys are being repeated as foreign keys in the fact table. One thing you would also notice that there are other words written next to it. It's PK. So all of these keys are also part of the primary key in the fact table. What that means is when you combine all of these fields together, then the combination is the primary key of the fact table, and it will help you uniquely identify just one row in the fact table. This is another example of a star schema. You can see that we have the product table, period table, store table, and sales is actually the fact table. This fact table provides the statistics for sales broken down by product, by period, or by store dimensions. And you will see that there are 3 measures here: unit sold, dollar sold, or dollar cost. This is the sample data for those tables, and you can see, let's take one of these. Let's say I'm interested in the first one. So one row here is the grain of the fact table. So uniquely identifying one single. So this combination you will see is unique in identifying one single row in this table. So these 3 fields together form the primary key of the fact table, that is the sales table. Let's make sure how these are connected. So product code 110 means, which is this one right here. So it looks like some shoes were sold. Period code 002 identifies here. It means it was the first quarter, 5th month of 2010. Store code S1 is here. So it looks like the store is called Jane's. It's in San Antonio. This is the phone number, and Burgess is the manager. So for this particular sales transaction, it looks like 30 units were sold and the amount of sales was $1,500 and the cost of the product was $1,200. So looks like there was a profit of $300, which is quite good. So that's how you connect the data across these different tables. Obviously, you don't have to manually do that. We will be using the joins in SQL to do queries like this.